Hello! So I've been doing nothing all day, apart from watching some YouTube videos and stuff. And I came across one of Adam Neely's awesome videos, and he was talking about loudness of different instruments and why orchestras need so many different violins to make sure they are loud. And I thought, well, there's some truth in this, but I thought I'd have a look. So here we go. We have sound awesome. Here we go. I've found it. So at 6 minutes 11 of his what's in between major and minor chords Q&A, which was a very good video. The question was, if two of the same instruments play the same thing at the same time, is it double the loudness? Now his response was...
Actually, no, which is kind of interesting because it goes counter to our intuition.
No, so... kinda. Okay, so I have this wave here, and it is what's called a sine wave, because what's happening is it's going up and down just continually. You can get different shapes of waves, you can get square waves and triangle waves and sawtooth waves, and so what happens is, just explaining some of the basics, so what we've got is the distance between here and this top bit here. It's called our frequency, so how quickly it repeats. And if it repeats really quickly, it's a
higher frequency.
If it repeats quite slowly, it's a
lower frequency.
Cool. And depending on the height of between the top and this zero line here, that depends like our volume. So if it's a really small wave, then it's going to be quieter. If it's a really big wave, it's going to be really loud. Cool. So we've got our wave here, and this wave sounds like this. So that's our wave that we're working with. I'll zoom back in. When I'm adjusting, so that you can see the adjustments of the width, but I'm just zooming in, so I'm just making it a bit wider. It's the same wave, but I'm just zooming in. Okay, so if we go, I'll play it again. So that's the wave that we are dealing with. So now what I'm going to do is let's get two waves and let's see how loud we think that is. Cool. So now I'm just going to play both. I'll mute one and then I'll play them both, and then we'll see, is it twice as loud or what's happening? It should be twice as loud, we think. So that's one, and with two. Okay, let's do it again. That's one, two. Well, it's a bit louder. I'm doing it again. Okay, well let's have a look at what's going on there. Okay, so what I'm going to do is I'm going to record that, and then we can have a proper look at what's going on. Cool. So now we've got our third wave here. Let me just trim the end. So let's have a look. What we'll do is we'll set them all to the same size, otherwise our scale won't work, right? Okay, well it's definitely bigger. Let me get my trusty ruler out. Let me see whether it's double, because we'd expect double the because we said if it's bigger, then it's gonna be louder. So we'd expect double the size to be double the loudness, surely. Okay, so let's measure it. Very scientific. Okay, so from the line, I'll probably draw a thing on. It is 6 mil, and then 1.2. 1.2. Well, that's good. So that's double, because it's 12 mil, it's double 6 mil. Okay, maybe it's to do with decibels. So let me have a think. So what I'm going to do is I'm going to loop it, and we can have a look. I'm going to mute them all though, so we don't hear them. We'll have a look over. It's not doing it, but we can see that. So we've got 0 on this one, on audio one, which is our double wave, and then we've got -6. We've got 6 dB difference. 6 dB. Okay, so let me see. It might just be the audio. So I'm gonna have a look. I've got a little dB decibel meter on my phone. So let me have a look, see if that is a thing. Cool. Okay, so I'm gonna do a little test. So I've got my little device here. Well, it's my phone with the app on, and what I'm going to do is I'm just going to play the waves to it and see what the thing is. Okay, so let me stop that. Cool, here we go. Here's the first one. Cool, so we've got a reading of 70, max reading of 70. Here we go. So let's see what 2 waves is going to be. Here's the second one. So that was 70. Cool. So we're getting, it's not the most accurate of devices, but it's sort of showing us that we're getting sort of the same sort of 6, 7 dBs, which is what we sort of expected because that's what the computer was saying. Okay, so it's showing a 6 decibel increase. But what does that actually mean? Well, decibels are a really strange scale that's used to measure the intensity of sound. And this is to do with the amount of pressure a sound wave carries and can actually exert. And due to the fact that sound is not like a physical thing that we can really hold, we measure it relative to other things. And this is similar to how temperature works, with the centigrade scale being relative to the boiling and freezing points of water. And in decibels, we compare everything to the quietest thing or lowest pressure that the ear can detect, which is around 10 to the power of minus 12 watts per meter squared. So if something is this powerful, we say it's 0 dB, or 0 decibels, 0 dB. And each power of 10, we go up by 10 dB. So if it's 10 to the power of minus 11, which is 1 higher than 10 to the power of minus 12, is 10 dB, and 10 to the power of minus 10 watts per meter squared is 20 dB, and so on. So as we can see, this isn't going up like a normal scale. As we increase one by multiplying by 10, the other increases by adding 10. And this is called a logarithmic scale and allows us to have a very large range of numbers contained into a reasonable set of numbers. Unfortunately, this scale, you'd think, great, we're trying to work out how loud stuff is, so surely that relates to our ears. But no, it's not. It's a very physicsy way of calculating it, and it doesn't quite relate to how humans, we perceive sound. So it doesn't really tell us that if we're doubling the decibels, that doesn't really result in a doubling of the perceived loudness. Because if we take an example, say we have a look at this number and this number, these are double each other, but this one is equivalent to a jet engine taking off, and this is equivalent to a whisper. So we can't really say that they are double the volume, because if you think that a jet engine is double the volume of a whisper, I don't think that's quite correct. So what does our 6 dB increase mean then that we had? Well, there's a few equations we can use to work these out. So if we plug our 6 dB into our equation, it shows that the sound should get 1.5 times as loud, which is sort of what I think we heard, because it wasn't quite twice as loud, but it wasn't sort of the same volume. It was a bit louder. So it was in between. So it's 1.5 times-ish as loud. And if I tell the equation now that we want to see how many decibels we'd need for our twice as loud perception. So we want to see how many decibels we'd need to achieve twice as loud in our ears, effectively. And if we do that, it turns out we need 10 dB. So why is it that our 6 decibel increase, which relates to twice the amplitude and intensity of a wave, doesn't mean that we hear it as twice as loud? Well, this is all to do with our perception and the inner workings of our ear. Psychoacoustics. Okay, so you've got hair-type cells in your inner ear, and these are called stereocilia. And these are arranged in the cochlea in order of pitch, starting at the outside with the highest pitch, and on the very inside, you've got the lowest pitch. Okay, and these cells are like the hair cells, and they're vibrating when the vibrations from the sound hit them. And that gets converted, this movement gets converted into an electrical signal out the other end, and gets converted into a signal that the brain can understand. And volume is achieved by having multiple of these hair cells at the same pitch. So because you've got the really high pitch over here and the low pitch over here, you've got sort of bundles of them that are the high pitch ones, and you've got bundles that are the low pitch ones. And if you've got lots of the high pitch ones, different amounts of these high pitch ones can move at the same time. So if you've got a high volume thing, lots will move, and if you've got a quiet thing, not many will move. Okay, so all of the hair cells that move at the same pitch will be added together, and their signals will be combined to add to the signal that's going to the brain. So you'll have a bigger signal if they've got more that are moving. So the brain has evolved originally to detect things that would impact its survival. So a small increase in sound intensity isn't going to worry us too much, whereas a large difference in sound intensity is going to alert us that we might going to die, or there's a lion going to attack us, etc. So the body's evolved to flatten out all of those sounds so that we can detect very loud sounds very easily, and sort of we don't need to worry about the ones that aren't that different in volume. So in the ear, a lot of the stereocilia will be vibrating quite a bit at a time, as you want the sort of highest quality of listening. Instead of having like a screen with 420p, you prefer to have like 4K. But we reserve the final few cilia for those really loud sounds, so that we can know that something's about to kill us, like the lion. So that's the reason why a twofold increase in amplitude or intensity doesn't result in a twofold perception of increase in perceived volume, because at the extreme there's say only one cilia that's going to activate, or two cilia, as opposed to the 100 say that have already activated. So you get sort of this sloping off effect, which result in less cilia being activated each time. So where does that leave us in terms of two instruments playing the same thing at the same time? Well, they're never going to be playing exactly the same thing. And if we go back to our waves, if you remember, we aligned them perfectly so that the peaks were lined up exactly. So the peaks were lined up, and then the troughs were also lined up. So the tops and bottoms were exactly the same time. But if we put the peaks in line with the troughs, then if we have a listen to that, there's nothing. And this is because we had lots of positive energy going together before. We've got the two peaks going together, but now the negative energy from the troughs is cancelling each other out. So we've got plus 10 at the one on the first wave, then we've got minus 10 on this second wave. That, when we add them together, is just going to be 0, and that's just going to be the whole way through. Just going to be 0, so no sound at all. And this can happen with real instruments to a similar degree. And you can see if we put any two waves together, some of the energy is going to be positive and some is going to be negative. So it may end up being quieter. So if the two instruments don't start their waves at exactly the same time, which is, if they did, it would be impossible, basically. If they don't start them at exactly the same time, there's going to be some of these issues. And also the reality is that two people playing are unlikely to be playing exactly the same pitch, as the tuning will almost certainly be slightly different, which will cause similar issues because we've got a longer wave going against a shorter wave, and that will lead to a crossing over of the positive and negative, which will cancel each other out to an effect. So in any respect, I think we've already shown that the maximum volume that can be achieved by two waves playing simultaneously is around 1.5 times the perceived loudness. So if that's the maximum, and there's a whole host of other factors that reduce the volume, it's just not going to be possible to get more than 1.5 times as loud. And so I think we can safely say that although two instruments playing the same thing could result in twice the intensity, it's highly impossible that we will hear it as twice that perceived volume. So I think Adam was basically right when he said that, it's not going to be twice as loud. It's possible to get twice the intensity, which is the sound pressure, but that is not going to be converted to twice the volume that we perceive in our heads. So I think that's just that. And I think my initial statement was wrong, and I'm quite happy to accept that. And I think it's been really fun to go into that and find out. And I hope you've enjoyed what this video will have become. I'm not sure what it's going to turn out as. But yeah, thanks. If you enjoyed this, I guess subscribe and like it. I don't know if there'll be any more videos, but if there are, then I look forward to them.